the Colóquio. Our first speaker this morning is Edelen from MIT, and he's going to speak about quantitative Reifenberg for measures.
Well, I first wanted to thank the organizers for inviting me. I've never been to South America before, but I think I'll have to come back. So I'm talking about a quantitative Reifenberg theorem for measures, and everything I tell you today is joint work with Aaron Neighbor and Daniela Valtorta. So the general question which we're trying to address is, suppose you have some set inside Rn, and you know this set satisfies some sort of k-dimensional affine approximation property. So you have some sort of k-dimensional affine approximation. And I'm being deliberately vague at the moment. But then the question is, given this, can you conclude that S has finite k-dimensional Hausdorff measure, and or sort of equivalently, can you conclude that it has a Lipschitz structure? So if you have a HK control / Lipschitz structure. Okay, and so I'll tell you, if you can hold off just a few minutes, like why this is interesting, why you should care. But we're first going to look at an example which sort of underlies several of the properties that we can expect. So this example, maybe I'll start it here, is the Koch Snowflake, which we all know and love. And I'm sure you know how to construct this. You start with a line, and you cut out more or less the middle third, and you replace it with the triangle. And in this construction, we're going to take this triangle of height eta. So normally you do like an equilateral triangle, but here we're going to do a small triangle. And then you have, if you adjust the width of the triangle, you have 4 segments of equal length, and each of these segments you repeat the process. So you scale down by a factor around a third, somewhere between a third and a fourth, and you put little scaled triangles, and you keep going, etc. And you get a sequence of these one-dimensional sets, and they limit in any reasonable sense you want to a fractal curve. And this is the snowflake. And it's not hard to show that even though each step in this process is sort of manifestly one-dimensional, the dimension of your limit, the Hausdorff dimension of this guy, let's see, I believe it's log of 1 over 4 divided by log of 1 over 4 plus eta squared. And that's strictly bigger than 1. Right, so for the classical snowflake, this would be log 4 over log 3, but if you have an eta, then it changes slightly. This isn't too hard to show. You just look at sort of how Hausdorff dimension is supposed to scale, and you play around. But so this is definitely not one-dimensional in the limit, but it still satisfies a pretty reasonable notion of affine approximation. And it satisfies the following property. So given any point in this set and any radius, let's say less than 2, then you can find a line depending on this point and radius. So this is a line, an affine line, such that the following holds. First, you know that in the ball of radius r centered at x, this set is contained in a very small neighborhood of the line. So S infinity inside this ball is contained in, let's say, the 2 eta r neighborhood of this line. So I'm writing, B sub r of something to be the r tubular neighborhood of this line. And then conversely, you can show that the line itself is contained in a small tubular neighborhood of the set in this ball. Right, and so you probably recognize these conditions together are equivalent to the Hausdorff distance of the set S inside this ball compared to the line inside this ball is less than to eta r. So the scale invariant Hausdorff distance is bounded by eta. Right, and so sets with this property are often called Reifenberg flat, at least provided eta is sufficiently small, because sets with this property were considered originally by a guy called Reifenberg back in the 60s. He was coming up with a different solution to the plateau problem, where he was considering minimizing via closed sets. And so, no additional structure like currents or anything. He imposed boundary conditions via homology. And at a certain point in his regularity theorem, he needed to say, suppose I have just some random closed set which satisfies a property like this. We could call it star. Then I want to say that it's actually topologically a manifold. So this is his theorem. It's a really remarkable theorem from, I think, 1960. It's known as the Reifenberg disk theorem. And it says if you have some S, let's just call it S, which is closed, and it satisfies star for eta less than some threshold, depending on the dimension and an alpha, so alpha is less than 1, then the conclusion is that in the ball of radius 1, this set is actually biholder equivalent to a disk. So there exists some mapping from RK. Okay, so I sort of switched from, this is one-dimensional, but it's true for k dimensions. You could phrase this where this is a k-dimensional affine plane. There's a mapping from RK to Rn such that you completely parameterize your set S in the ball, and you're biholder to this plane. So that says like 1 plus c eta x minus y to the 1 over alpha is less than phi of x minus phi of y is less than 1 plus c eta x minus y to the alpha. Right, so you're with a very good constant too. And what's really crazy about this theorem is that it's telling you that you can have sets which are biholder equivalent to a line which themselves have Hausdorff dimensions strictly bigger than 1. Right, so biholder equivalence is very weak and it doesn't even preserve Hausdorff dimension. It's a really neat theorem. So let me just tell you briefly the idea behind how to prove it. It's actually very simple. Making it work is a little tricky, as you might imagine, but the idea is simple, and it actually uses only very elementary tools. And so you construct a sequence of k-dimensional manifolds, okay, and each manifold is going to be the image under some map, so you're actually constructing the maps. And these guys are going to limit in the Hausdorff distance to your set S. Okay, so then, how do you construct these manifolds? What you do, you start in a ball of radius 1, and this condition tells you that your set is well approximated by some line or some plane. So you have some line, and your set's like very close to it. So you take T naught to be this plane or line. And now choose some scaling factor, like rho, to be like 1 over 10. And then your next scale is going to be rho. So what you do is you take a Vitali cover of your set of balls of size rho. So like, balls of size R1, which is rho, the 1 which is 1 over 10. Okay, and each one of these balls, you're well approximated by some plane. And this Reifenberg condition tells you that essentially nearby planes only tilt by an amount eta. So if you move up a few scales or you move across a few points, your planes can only tilt by about eta. And so that means that you can essentially interpolate between these planes. You take sigma to be like a glorified interpolation of projection mappings. And then you take T1 to be a sort of interpolation of these planes. And then you repeat the process. In each one of these balls, your next scale is rho squared. So you take a Vitali covering of your set S, and then you have a best plane, and the planes only tilt by eta, and then you take an approximation, and you build up these TIs as sort of like interpolations of planes. And they locally have very good like Lipschitz structure because of this property, but as I goes to infinity, they just barely fail to preserve the Lipschitz by Lipschitz. And so because they sort of fail by just a factor of eta, you can get polar. So anyway, it's a pretty cool theorem. If you have nothing to do someday, you should look it up. But I'm gonna, let's see. I want to bring your attention to two properties. So the first is that alpha is always strictly less than 1, right? This theorem completely fails. You can never get alpha equals 1 unless eta is 0, right? And this example sort of illustrates that. And in particular, you can never get measure control or Lipschitz structure. But the other thing is that this Reifenberg condition it's like a two-sided L infinity condition. You're saying that I have to be in a small neighborhood of the set, or the set has to be in a small neighborhood of the plane, and the plane has to be in a small neighborhood of the set. So that rules out a priori holes in S, right? Because if you have a big hole in S, then a small neighborhood is not going to be close to it's not going to contain a plane. But it also rules out excess sets. So you could imagine a scenario where like most of your set is very close to a plane, but you have some fairy dust, scattered around, which you don't really care about because maybe you're interested in like rectifiability, and this doesn't allow for that. And so what we're really after is some sort of theorem which allows for holes in excess sets and gives us measure control and Lipschitz structure. But it's going to build on Reifenberg's theorem. Okay. Does anyone have any questions? Okay. So we're going to go back to this example, the snowflake example, and we're going to look at sort of why the measure control fails and like what sort of is a natural condition that guarantees this measure control. And okay, I'm going to erase this stuff here. So another way of seeing this failure is that if you look at how the length of this curve grows as I goes to infinity, it's easy to show that the length of each SI is approximately 1 plus eta squared to the I. Because at each stage you're bumping up by factor eta, and then Pythagoras gives you the square root of 1 plus eta squared. Right? And so this goes to infinity. But now, suppose we were to modify our snowflake construction by instead of having a fixed eta at each scale, or scale invariant eta, you change eta with your scale. So this is eta 1, and then this is eta 2, scaled by a third, and then this is eta 3, et cetera. And then so if you have a modified snowflake, then by the same logic, the length is approximately the product of 1 plus eta j squared from j from 1 to I. And this is basically e to the sum of eta j squared. So it's telling you that somehow if the tilting of nearby planes is square summable, then you should have, that should be enough to give you measure control. And this condition is sort of the key condition which arises all over the place. Sort of it's like a Dini condition, square summability of tilts. And I'm not really sure who was the first person to figure this out. One of the most famous papers, one of the first and most famous papers which uses this is a paper by Peter Jones from the 1990. And he proves what's called an analyst traveling salesman problem, where he's trying to figure out a reasonable condition to impose on some set in the plane, which guarantees you could contain it in a connected rectifiable curve, right? It's sort of a traveling salesman. And then he defines something called the beta number, which we're going to define in a second. And this kind of condition on the beta numbers is precisely the condition which allows that. So he had this, a 1D traveling salesman. And so our theorem, which I'll tell you soon, is you could sort of view it as a k-dimensional version of this traveling salesman problem. Okay, so let's erase this. Okay, I'll give you one and a half more reasons why this is interesting, then I'll tell you the theorem. So a stronger motivator is actually a really amazing theorem by Neighbor and Valtorta, where they use the beta numbers, which I forgot to define. I'll define them now. And they prove Lipschitz structure on the singular set of minimal surfaces, right? Which they prove quantitative Lipschitz structure on the singular set, which hasn't been known before. So I forgot to tell you the beta numbers. I'm sorry. So our notion of affine approximation is going to be the following. So for a set S, you define the k-dimensional beta number at some point at scale to the infimum of affine planes, of affine k-planes of 1 over r to the k, integral br of x intersect s, of the distance to this plane squared, 1/2. Right, so Reifenberg's condition is a two-sided L infinity condition. This is a one-sided LP condition, right? So it's sort of like the most obvious thing you could write down, which would allow for holes in excess sets. And then you could similarly define, the beta number for an arbitrary measure, where you just integrate against the measure instead of the Hausdorff measure, right? So this is the notion of affine approximation we're going to use. Okay, sorry. Right, and so let me tell you about their theorem. So Neighbor-Valtorta proved the following in a paper in, I think, 2016. They showed if you have an n-dimensional codimension 1 area minimizing hypersurface, so area minimizing, then it's been known since the work of Federer and Jim Simons that the singular set has codimension 7, but they actually proved that the singular set has finite n-7 Hausdorff measure for any point in R, and it's n-7 rectifiable. So they even proved more. They proved that it satisfies a sort of uniform packing bound, like a uniform Minkowski estimate, which is much stronger. But this is a really remarkable theorem, partly because there have been very few progressions in the understanding of the singular set. There have been some really big theorems, but very few of them. And so, it's been known since Federer and Simons that, from the 60s, that the dimension of the singular set is at most n-7. And then Leon Simon in the 90s, I can't remember exactly which year, he has an amazing paper where he proves that it's rectifiable. So n-7 rectifiable. But he needs that the ambient manifold, you can do this in ambient manifolds. He needs that the ambient manifold is analytic, because basically his way of getting tilting control is using the Loy-Shavitz inequality instead of like a Reifenberg process. And he isn't quite able to get measure bounds. So he has further restrictions, but on the other hand, his theorem tells you more about the tangent cones. Like his theorem tells you almost everywhere uniqueness of the tangent cone, whereas this only tells you almost everywhere uniqueness of the spine.
The ambient manifold must be complete? Or?
Yeah, so let's say complete, but you only need something like C2 or C3. In like very brief words, the starting point of Neighbor-Valtorta is the following inequality, and it says that if I have some radon measure, and it's supported inside the singular set, then I can conclude that the n minus 7 beta number at any point in scale is bounded by constant over r to the minus 7, the integral of the density drops of m. Just give me a second, I'm sorry. Oops. C du. Right. Okay, so what these are, this here is the density ratio of your minimal surface, right? It's the n-dimensional Hausdorff measure of m normalized, right? And there's a classical result which tells you that this is increasing in R, or at least almost increasing if you're in a manifold. And so what this basically tells you is that the beta number is controlled by the density drop at a given scale, and so with a certain amount of work, you can show that the integral of the sum across scales of these beta numbers squared is bounded, right? Because essentially, this is the density drop, and the density is monotone. So if I sum over scales, I'm going to get a telescoping series. And so this is giving you precisely the sort of summability condition that we see here, which should guarantee you finite measure control. Right, and so from here you get some sort of bound, like an L1 bound on the beta numbers like this, and then you can, from there you get to here. Like this inequality is actually not too hard, but getting to here is like 70 pages. And so what we did is trying to sort of refine and generalize the theorem which goes sort of from here to here. Okay. So I'll tell you our theorem. Well, let me also just remark, sorry, I keep sort of leaving you in suspense. There's also, sort of interestingly, there's a strong relationship between these beta numbers and Calderon-Zygmunt theory, where somehow there's an equivalence of if you have some measure with some very weak properties, then like general Calderon-Zygmunt operators are bounded if and only if you have some sort of beta number control like that. So these also arise a lot in harmonic analysis. All right. So the theorem with Neighbor and Valtorta is the following. Suppose you have some just Borel regular measure, and you take some epsilon non-negative, and suppose you have some sort of L1 control like that. You know that the integral of the sum of the squared beta numbers is finite. Right, so here I'm summing over scales. Then the conclusion is that there exists a closed K rectifiable set S such that I have measure control away from this set, and I have like Hausdorff bounds. I have packing control on this set. So this is the K-dimensional guy. And then lastly, I have a sort of non-collapsing on the set S. So for all x and S. Right? So somehow, like for a general measure, you have to kind of split it up into a region with really high density and a region with low density. But somehow the region with high density still has packing control. Okay, and then a sort of easy corollary of this is that if your measure is the Hausdorff measure restricted to some set, then you can conclude that that S is actually just rectifiable and with measure bounds, bounded by some constant. And then similarly, you know, if mu is what's called a packing measure, which is a really important notion where you essentially sort of discretize a Hausdorff measure, then you can just conclude that you have a finite measure. So then U1 is finite. And so what a packing measure, what you do is you say, okay, suppose I have a collection of balls which are disjoint. And then the packing measure is some measure of the form, you know, R alpha to the K times the indicator function, or times the Dirac delta at X alpha. So you sort of like discretize. And this is actually an incredibly important notion because the way you prove this measure bound from an inequality like this is using a packing measure. You have to kind of discretize it. Yeah.
I don't quite understand why you ask conditions on B1 on the pole of -1. The first condition that you wrote is mu of B1 minus S.
So this is just the sort of,
Why B1?
you could pick any ball. So here, this is just like, suppose I have some measure supported in the ball of radius 1, then I want a condition on the whole ball. You know, you have to localize it somewhere.
So it's not the same as asking or equivalent of asking S to be compact or
So S,
inside B1 because you have no control outside of B1.
so S, okay, so S is going to be compact. Like, I mean, yeah, you can show S is compact. But like, I mean, this is just, you know, like picking some scale to work. Sorry?
Your measure is localized on B1.
Yeah. Because, like, this is really like, both of these theorems are sort of local in the sense that you pick some scale to work at, you know, and then you work in that scale. So, right, so this is sort of a generalization of the Reifenberg type theorems which they use to prove this result. Okay, and in the last like 5 or 10 minutes, let me just give you a brief idea of how the proof works. So there's sort of 3 key ingredients. One is kind of an observation, the first one. And your initial observation is that because the beta number, it's an LP condition, that means that somehow the big mass region is always concentrated near some plane, right? So if I write like V of XR to be the plane that realizes beta of XR, then if I look at the region any sort of fixed distance away from this plane, I can bound the measure in terms of the beta number, right? So I can bound the measure inside this ball minus like some neighborhood of the plane by root minus squared, the beta number at this scale times r to the k, right? So somehow like the big mass region is near k-planes. So somehow, like, the really hard part is getting a bound like this on the high-density region. Because once you have a bound like this, then you can control the measure sort of away from it via the summability of the beta numbers and the measure control in S. So for all intents and purposes, we are in the scenario where we have some set where at any scale we look close to a k-plane, but we're not quite in the Reifenberg condition because we don't know the converse. And this is actually a really big issue, because in order to get that tilting control, in order to be able to say that planes, nearby planes only tilt by eta, you need to know that you actually look k-dimensional, not just that you're contained in the k-plane. And so the other point, the second point, is that we need to know, so we know that the nearby planes tilt by, the tilting is controlled by beta of xr, provided your measure looks k-dimensional. Right, so I want to be able to say that if I look at the L2 best plane at one scale, the L2 best plane at another scale, then they only tilt by amount controlled by beta. Because then this summability condition will tell me that the tilts are square summable. But in order to get this, you need to know that you look k-dimensional. And the reason is illustrated if you think about a really simple example. If your measure or your set's actually like k-1 dimensional, then you have a sort of whole one-parameter family of possible L2 best planes, right? Your L2 best plane is not uniquely determined. And so, if at this scale you look k-dimensional, and then this scale you look k-1 dimensional, then there's no reason, like, why should you happen to pick the good plane that tilts very little compared to this one? Does that kind of make sense to people? Like, if I have a line and I'm asking, like, what's the best plane, then, like, there isn't a best plane. I could choose any of them. And so you really need to know, not only am I contained in a k-plane, but I actually really look k-dimensional in order to get this tilting control. And so precisely what that means is that I'm asking that I have, in this ball, I have k+1 points, where around each point I have a very definite amount of mass, right? Because each one of these points, if it has a lot of mass, it's going to have to be close to the k-plane. And that's what allows me to control tilting. Okay, and so, we're in almost good shape because we're in this scenario where if I know, like, a priori I look really k-dimensional in all balls, then I can get tilting control and I can use a sort of Reifenberg process to get this bound. But I don't. So I have to think, okay, what happens if I don't look k-dimensional? But something really silly happens if you're not k-dimensional. You look k-1 dimensional. So you look k-1 dimensional. But if you have some set which looks k-1 dimensional, then it's really easy to obtain really small k-dimensional bounds on it. Right? So you can obtain small k-dimensional packing bounds. Just because I'm one dimension off, right? So of course I'm going to get really good packing bounds. And so now I have this sort of dichotomy where I can play these two processes off each other. I have the good process where if I hit a ball and I look k-dimensional, then I have tilting control and I can use a Reifenberg process. And I have the bad process where if I hit a ball and I don't look k-dimensional, then I actually look lower dimensional and I can just do a stupid covering argument and get the packing estimate I want. And so you alternate these processes, sort of very similar to how the Reifenberg theorem works. So I start in some good ball, I have some best plane, I cover it with balls of the next scale, like R1, row to the 1, and then if these are good, I keep going. But if it's bad, I just stop. It's like a stopping time argument. And so, this is good, I keep going, this is bad, let's say this is bad. And so I keep sort of working my way down as much as I can, but I have to stop whenever I see a bad ball. But then when you see a bad ball, you can do this process in reverse, where you have like a best, k-1 plane, you cover it, you stop if you see a good ball. And then you end up building this tree. So if this is your scale, so like this is a good tree, for example, and you have to stop. You have to stop at bad balls. And these are all bad. But then you can rebuild. At these guys, you can start bad trees. And then, so these are now bad trees. And then here you start good trees, and you sort of alternate these trees. And in this way, you can work your way down and get a covering by smaller and smaller balls, and eventually get the Hausdorff bound you want. So it sort of works out nicely. And there's only one sort of subtlety, which is that every time you build a new tree, you get a double counting error, because you forget the fact that you've built other trees. But you're saved because your small packing bound, you gain a factor of rho. So remember, rho is your choice of scale. And so every time you switch trees, you're going to get a factor of rho. And you can choose your rho in such a way that it kills the double counting error. So somehow it all quite fits together. Yeah, so if you're familiar with harmonic analysis, there's a very strong analogy between this sort of construction and a corona decomposition. And so this is sort of also where you can start to see the harmonic analysis parallel. But anyway, I think I'm pretty much out of time, so I'm going to stop here.